In this video, we'll be discussing rotational kinematics. Starting off with the concept of rotational motion, we recall the formula for arc length. The formula for arc length is arc length x is equal to r times theta, where theta is in radians. When we rearrange this equation, divide r on both sides, you'll get that your angle is equal to x over r, or the ratio of x. Arc length, ratio of your arc length over your radius. So your angle theta can be in radians but also in revolution. Take note of the conversion, that one revolution is equal to 2 pi rad, or in degrees it's 360 degrees. So the whole rotation, the full circle. We will be relating our linear and angular values. In our linear or translational values, we have x as your displacement, then v for your velocity, and then a is for your acceleration. Okay? Take note that in angular or in rotational motion, your displacement becomes angular displacement represented by theta. Then your velocity will become your angular velocity, denoted by the small letter omega, and then your acceleration as your small Greek letter alpha. Take note of the relationship as we defined earlier. Your arc length, which is x, which is also your displacement, is equal to r times theta in radians. So in your velocity, in your linear and your angular velocity, is related by velocity is equal to r times your angular velocity. Then acceleration, your linear acceleration is equal to your radius times your angular acceleration alpha. Let's take a look at your rotational kinematics. Remember your three basic equation in the single dimension motion, or motion in one dimension, or simply your kinematic equations. This is also similar to rotational kinematics. It's just that we change the linear values to angular values. So you will see their similarities. The first equation in your linear or straight line motion or kinematics is actually v sub f, our final velocity, is equal to initial velocity plus acceleration times time. Here in rotational kinematics, where we have a fixed axis rotation and constant angular acceleration, we have your angular velocity, final angular velocity is equal to initial angular velocity plus angular acceleration times time. This is actually your similar to your equations 1, 2, and 3 in your linear kinematics. So here are your variables. So we have your final angular velocity, which can be in radians per second, radians per minute, or revs per second, revs per minute. We have your initial angular velocity of the same units because they're the same variable or same quantity. It's just that it is recorded or measured initially. Then you have your angular acceleration. So basically, this will be in the unit of radians per second, radians per second squared, radians per minute squared, or revolutions per second squared, or revolutions per square minute or minute squared. Then you have your angular displacement, which is definitely in radians or revolutions, and then t is your time. Let's try some examples. Okay, so example number 1 reads, you have an industrial mixer blade which rotates at 2,400 revolutions per minute or RPM. You're asked to compute the blade's angular velocity in radians per second. How many seconds does it take for the blade to rotate through 120 degrees? Assume your constant angular speed. So you were given 2,400 revs per minute. And then you were asked for your required the angular velocity in radians per second, and then the time for theta to become 120 degrees at constant acceleration. So for the first one, for letter A, to solve, we just need to convert 2,400 revolution per minute using your conversion factors that in every 1 minute there's 60 seconds, and then in every 1 revolution there is 2 pi radians. So this will cancel out. You'll have radians per second, so this will be 240 divided by 60. So this will be 40 times 2. So this will be 80 pi radians per second. So this is your answer for the first one. Next is we have how many seconds would it take for the blade to rotate through 120 degrees. So again, as you mentioned, your pi should be in radians. So you first turn 120 degrees into radians by dividing 180 degrees to pi. Because 2 pi is 360 degrees. So from degrees to radians, we'll use this conversion factor. So this will then be 2 pi over 3 radians. We will use this in the, since we're asked for the time, and then you were given your, velocity, the 2,400 revolutions per second. So we can use this to solve for the time. We can start with the given 80 pi rad per second. So we can just simply divide 2 pi over 3 radians and divide it with 80 pi radians per second. That gives you an answer for seconds. So pi will cancel out. Then you'll have 2 over 240 or 1 over 120 seconds. This will be your final answer. That is for example number 1. Let's have example number 2. So example number 2 reads a flywheel requires 3 seconds to rotate with an initial angular velocity of 48 radians per second and its constant angular acceleration is 20 radians per second squared. What is the angular displacement of the flywheel in radians and also in revolution? So we start off with the given. So you're given the time, 3 seconds. And then you're given your initial angular velocity, of 48 radians per second, your angular acceleration of 20 radians per second squared, and then you were asked for the angular displacement. Take note of the angular or rotational kinematic equation number 3, that your angular displacement is equal to the initial angular velocity times time plus 1/2, then your angular acceleration times time squared. So we just substitute the values, then we can get theta. So this will be 48 radians per second times the time, 3 seconds, plus 1/2 angular acceleration 20 radians per second squared. Then you have 3 seconds, then squared. Cancel out this will be squared. Solving for the value of theta, you'll get 234 radians. To get the radians also in revolution, we just divide it with the conversion factor. 1 revolution is 2 pi rad. So it will be 234 over 2 pi rev, or 37.242 revolutions. That is for example number 2.